Hello, I am Fritz Haber, also known as Alvin Bratz. Here's my assistant, Robert LeRosignol, and I also worked with.
Carl Bosch. You can also call me Raven Brown. And my assistant was Alan Matash. And together we established the Haber Bosch process, which we truly think was the pinnacle of contemporary society.
So, nitrogen makes up about 75% of the atmosphere. Well, if it makes up so much of the atmosphere, why is it so hard to use? To make in usable form. Well, nitrogen exists as a diatomic molecule that is triple bonded to itself, meaning it is very thermodynamically stable, which makes it very hard to react with hydrogen to make ammonium, making it usable for fertilizers and bonds and whatnot.
So there were some prior sources of harvesting usable nitrogen in our society. So one of the first prior sources were nitrogen fixation, which is the natural process of converting free nitrogen into nitrogen products, such as ammonia, nitrates, and nitrogen dioxide. And so these nitrogen products are then used and incorporated into organic compounds. And since this nitrogen cycle happens naturally, this process takes a long time for our society to harvest it. Um, and so another prior source was the Chilean saltpeter mines, which is where Germany, like specifically, was harvesting their nitrates for use. But it was later realized that these nitrates were non-renewable, especially with respect to society's exponential growth. And in Figure 4 is pictured the Chilean saltpeter mines below.
So, here's the chemical equation for the synthesis of ammonia. And paying attention to Le Chatelier's principle, we can see that there are less moles on the product side of the reaction than there are on the reactants. So as we increase pressure, the side with less moles will increase. So more ammonium is produced as pressure is increased. And since this reaction is exothermic, as temperature decreases, you would think that more products are created. However, you need a catalyst to operate at such a low temperature. Well, however, the catalyst does not operate at a low temperature. It operates at 380.
So Fritz finally established the process. So along with his assistant, Robert LaRosignol, they developed these high pressure devices that could catalyze the production of ammonia from free nitrogen. So once this process was established, the German company BASF purchased the process and assigned myself, Carl Bosch, to industrialize it. So since I was on the project, I brought in my assistant, Alan Matash, who later realized that there was an iron catalyzing potential that could be far more efficient for this reaction and increase it to an industrialized scale. And in Figure 6, the original tabletop paper device is pictured.
So, yep, a catalyst was born. Fritz Haber's original tabletop machine only produced about a cup worth of ammonia every 2 hours, and it used an osmium catalyst to produce this. Now, seeing as osmium is one of the rarest metals on Earth, it is not practical to use it for such an inefficient form of ammonia production. However, Carl Bosch worked to to make this commercially available by replacing the osmium catalyst with an iron catalyst lined with various other metal oxides to grab the nitrogen molecules out of the air and hold them to the catalyst surface. And this catalyst lowers the activation energy of the synthesis, meaning less energy is required to complete it. And this iron catalyst is heterogeneous, meaning that since the catalyst is solid, the reactants that it is catalyzing are gaseous, which are in different states of matter.
So let's dive in a little deeper into how this iron catalyst actually works. So as we mentioned earlier, nitrogen is a diatomic molecule, and how it bonds to itself is through a triple bond. And this triple bond is one of the strongest possible bonds that can exist. And that is the problem that we face when trying to harvest nitrogen, because it's so difficult to break that triple bond between the nitrogen.
So yep, this iron catalyst it causes the nitrogen to break from the diatomic state into its individual atom, and it is triple bonded to the surface of the catalyst. So it's adhered to the catalyst.
So now we see that the nitrogen is now double bonded to the iron catalyst, which is now less thermodynamically stable, which therefore makes it easier to react with the hydrogen.
Now it is single bonded to the catalyst, which makes it even more thermodynamically unstable and easier to react with the single hydrogen left.
So now we see that the ammonia product is fully adhered to the catalyst and is now ready to break off.
Broken off, now the ammonia molecule has freed itself from the adhered surface, and the process repeats with each individual atom.
So let's take a closer look on how this Haber-Bosch process is manufactured. So first we'll start with the production of the synthesis mixture. So we'll react methane and water is introduced into the system, and they react with one another, and that creates 3 moles of hydrogen gas and a byproduct of carbon monoxide. Air, which is mostly composed of oxygen and nitrogen gas, are then introduced into the system, reacts with our elements, and then creates 4 moles of hydrogen gas with a byproduct of 2 moles of carbon monoxide. So now we are left with nitrogen gas, hydrogen gas, and carbon monoxide. This travels to the catalyzer where water is introduced, which reacts with the carbon monoxide to create carbon dioxide, and our nitrogen and hydrogen gas remains. We travel through the catalyzer one last time, and water is introduced again, and that creates a byproduct of water and carbon dioxide, and we are finally left with nitrogen and hydrogen gas, which is what we want. So this now travels up to the heater, which is where a very important part of this entire process occurs. So we mentioned earlier that this whole entire process is driven by Le Chatelier's principle, which favors the side of fewer moles, which in our case is the product side. So in an ideal world, we would want this reaction to go very fast. So to make that happen, we would have a low temperature and a high pressure to really increase the production of our product. However, many facilities cannot withstand these high pressures, and there is an example of what happens when we don't have a facility that can withstand that. So this is the Alpau plant in Germany in 1921, and this plant exploded because they did not have the proper facilities to withstand that pressure and low temperature. So we introduced a compromise temperature and pressure, which is a 380 degrees Celsius for the temperature and 200 atmospheres for the pressure. So once the nitrogen and hydrogen gas go through the heater and into the reactor, they then go to the waste heat boiler, where water is introduced one last time and steam is let up. And so now we are finally left with nitrogen gas, hydrogen gas, and ammonia, which then travels to the cooler, where ammonia becomes liquefied, and we tap it off, and we have our ammonia fluid. And this yield is about 10 to 20%, which at first sounds very low, and it is a very low yield. However, the nitrogen and hydrogen gas can then be reused and through the cycle once more until there are no more moles of nitrogen and hydrogen gas.
Yeah. Now, with this recovered ammonia product, why do people want it? Well, because synthetic ammonia is used to make nitric acid. And the important thing about nitric acid is it is an important precursor to most explosives at the time. And seeing as Germany was blockaded by the saltpeter mines, were blockaded by the Allies, the Germans had to find an alternative source for this. So synthetic ammonia gave them plenty of firepower, and it also allowed them to have a fertilizer for their crops. And in the bottom left figure, you'll see as the ammonia content in these soils increases, the fruitfulness of each crop increases, and you don't want a skimpy crop. So you're going to want to invest good nutrients into it.
Yes, and finally, so at the beginning of our presentation, we stated that this process is the pinnacle of contemporary society. And that was a very bold statement for us to say, because there were many innovations that occurred, and like many could be the pinnacle. But we classified our process as the pinnacle because of the lasting effects that it had on our society. So one of the effects is the high pressure systems innovation. So before this process was established on an industrialized scale, there really weren't many high pressure systems that could produce, that had like such a mass production that this process has. So this really served as an example for future innovations that really wasn't there beforehand. And also, this now was a sustainable source of usable nitrogen. So as we mentioned earlier with using the Chilean saltpeter mines, that was a non-renewable source of nitrogen. So especially like since our population was growing so quickly, so rapidly, that mine would not last longer and definitely could not withstand the population growth that we were about to face. And so that brings me to this graph, figure 11, which shows the world population supported by synthetic nitrogen fertilizers. And since our population is about 7 billion, or a little over 7 billion now, without the synthetic nitrogen fertilizers, we would only be able to feed about 3 to 4 billion people. So the gray area of this graph shows the population supported without the synthetic nitrogen fertilizers, and then the coral part of the graph shows the population that was supported by the synthetic nitrogen fertilizers. So because of this invention, we are allowed to thrive like we are today. And so that is truly why this process is the pinnacle of contemporary society. Yes, thank you.
Here are our sources. Thank you for your time. Woo!
Yeah.
Yeah. Yeah. Oh, it's still recording.
Oh no.